Okay, now we're going to take a little bit of a detour and talk about something that a lot of times students get very confused about. But it's actually not that difficult. So hopefully I can explain it to where you understand it. And that's the concept of domain and range. Now actually, when we talk about domains and ranges, for us, we need to talk about it in the context. Oftentimes you'll have a graph, and they'll say, here's this graph. What's the domain and range of the function on this graph? But then a lot of times you'll have an equation or a function, and they'll say, here's this function. And usually with the function, the main thing is the domain. With the graph, they like to ask for domain and range. Normally when you have an equation or a function, they'll mainly ask you about what is the domain. So let's first talk about the idea of how to determine the domain and range when you're given some kind of a graph. And this is actually not that difficult, actually. It's easiest just to do some examples. Say, this is a pretty standard function. So there's some kind of a function, some kind of equation graphed out. First of all, when you have a graph, normally it's pretty common, domain and range oftentimes you'll give it an interval notation, not every time, but it's pretty common. So we have to talk about, remember what intervals are. Intervals are either parentheses or it could be brackets where it's like the low number to the high number, right? So an interval is like the answer is a whole range of numbers. And basically what you say is, okay, the answer is a whole range of numbers. So I'm going to give you the lowest number in the range and then the highest number in the range, or I shouldn't say range, interval. How about this? Say the answer is a whole interval of numbers. So the way I'm going to do it is I'm going to say the answer is, here's the lowest number in the interval, and here's the highest number, and I write that as an interval, and the solution is everything in between. That's one of the ways you like to do domains and ranges. So, first point is, when you talk about domain, domain is associated with X, and range, we're talking about Y. All right, that's very important. When I first learned domains and ranges, I said, how can I remember which is domain, which is range? Well, how about think of the alphabet. Domain D comes before range R, just like X comes before Y. So if I'm asked to find the domain and I think, okay, is the domain X or Y? Then I think, well, it's either domain or range. Oh yeah, domain comes before range, like X comes before Y. Oh yeah, domain must be X. Now here is my definition of domain. And this may seem not quite, doesn't make sense at first. Since domain has to do with X, I say the domain are the list or the interval or somehow however you express it, basically all the possible values of X. What numbers can X be for my function, for my graph, for my equation? So let's think about that with our first example. So X is like my horizontal axis. This graph at each point I have a value of x. Now you notice here the arrows, so this looks like this graph goes on forever, sort of this direction, and it goes on forever in this direction. So it, in a sense, it keeps getting wider and wider and wider. If I'm asking for the domain for this graph, basically what I'm saying is, let's go look at this graph, and what, if I'm thinking about x-axis moving left and right, if I go to the left, because these are my small numbers, my negative numbers, what's the smallest value of x where this graph exists? Where is it, like at, at minus 10? Is the graph, does it exist when x is minus 10? Yeah. How about minus 20? Does it exist? Yeah. How about minus 100? Matter of fact, how far does this graph in effect go? Well, if it goes on forever, we like to say this graph goes clear to when x is negative infinity. So what's the smallest value of x for this graph? Negative infinity. And in the same way, what's the largest value? If this goes up, but it keeps going to the right, how far out does this graph go? What's the largest value of x? What's the farthest to the right this graph is ever going to go? Well, it's going to be positive infinity. So for this graph, you know what the domain is? It's the interval from negative infinity to positive infinity. That's the domain of this graph. It's an interval. In this special case, sometimes people like to say all real numbers, because you notice every number x can be is included here. Now just to look at the range, since the range are the y's, now y's we're thinking up and down. So I say for this graph, what would the range be? So what you do is you ask yourself, what's the farthest down? What's the smallest value of y for this graph? How far down does this graph go? Well, for this one, once again, because it's continually going down, looks like it's probably negative infinity. And how far up does this graph go? What's the largest value of y for this graph? Well, it's continually going up. So it looks like the range is also negative infinity to infinity. All right, let's do some different kinds of graphs, maybe with a little bit of twist. How about we have a parabola? Now, first of all, over here, whenever you have infinities in an interval, you always make infinities with parentheses. Because parentheses with intervals means like you never quite get to the value, and brackets means you're actually at the value. Infinities are always with parentheses. So let's find the domain and range of this graph. Domain. So this is a parabola that gets wider and wider as it goes up. So domain, all the values of x, the possible values of x. So if I look at this graph, what's the smallest value of x where this graph exists? How far to the left does this graph go? Well, it goes forever. So it must be negative infinity. How far to the right does this graph go? So once again, it looks like the domain is negative infinity to infinity. How about the range? So the range is up and down. So now I start with the lowest value. How far down? What's the smallest value of y for this graph? Well, if I look at it, it looks like this graph goes to 0 and then turns around and starts coming back up. So what's the smallest value of y for this graph? It's going to be 0. And because the graph actually touches 0, I say the smallest value with a bracket is 0. Now what's the highest? What's the largest value of y? that this graph goes to. It keeps going up forever. So those are the basic ideas of domain and range. But now let's do a few more little sort of complicated graphs. Now notice these two examples. We say that these graphs are continuous. There's no breaks or gaps. It's just like one line here. It's one curve. But you don't always have that. Here's a very common graph that you have sometimes. Oftentimes you have graphs and they're not continuous. In other words, it's not just one line that's connected. You may have something like this. Now here's another concept I need to introduce in terms of graphing and later on with equations. And that's the whole idea of these things called asymptotes. Asymptotes on graphs are dashed lines, and it's almost like, asymptote is almost like an electric fence. I mean, you can't touch it, you can't cross it. In other words, for this graph, I actually have an asymptote. It's almost like the y-axis, so I draw it next to it. Because what happens is this graph, as this goes up, it gets closer and closer and closer to the y-axis, but it never, ever actually touches the y-axis. It gets super close, but it never touches it, because this is an asymptote. And the rule is, the graph cannot cross or touch an asymptote. And as it goes down, once again, it gets very close to the y-axis, but still never touches it. And actually, we have what we call, so this is called a vertical asymptote. Vertical meaning it's a vertical line. Vertical means up and down. We actually, in this case, also have what's called a horizontal asymptote. Same idea. As this thing, as x gets smaller and smaller, the graph gets closer and closer, but it never, ever, ever touches or crosses this asymptote. And up here, it's the same thing. This is called a horizontal asymptote. So now, based upon that, someone says, what's the domain and what's the range? Well, if you weren't being careful, for the domain is like the smallest value of x, the largest value of x. If you just looked out here, you say, well, the smallest value of x is negative infinity. And then here, the largest value of x is negative infinity. So someone might say, well, it looks like it's negative infinity to infinity. But that's not correct. Why? Because we're saying every value in between negative and infinity is part of the domain. But you know what? What happens when x is 0? When x is 0, it's not part of the domain. The graph, there is no graph when x is 0. It gets close, but it never actually gets to x equals 0. So really, it's like what I'm saying is, well, the domain should be negative infinity to infinity, except for when x equals 0. Well, how do we write that? Well, there's a couple ways. One way is we can write this as two separate intervals. Whoops, as two separate intervals. Let's do this one first. We know the domain goes from negative infinity and it goes up until 0, but with the does not actually get to 0, so the parenthesis means it doesn't quite get there. But then I have this piece also. and I do a thing called a union, where I basically take this interval and sort of combine them. So this one, now it starts at 0 and it goes to infinity. So this is one way they sometimes like to express this. But there's actually another way where they sort of do what's called set notation. Because really, you know what's going on here? What's my domain? I could say all real except x equals 0. There's really only one value of x that is not in the domain. And that's right here where this vertical asymptote is, when x is 0. Every other value of x, I've got the graph here. So this is another way, sort of in words, they like to say it. But then the last thing, which I think sometimes they might want actually in your MyMathLab, set notation is this funky notation. You do these squiggly brackets and you say x such that, and what you do is inside here you simply write down what x cannot be. So this is another way of saying all real except x equals 0. This is another way of saying this interval right here. Now if we talk about the range, it's the same idea. We have this break here when y is 0. So in this case, I could say the range, if I want to use this notation, this means the range is everything except when y equals 0. How about if we had, while we're here, let's talk about asymptotes, because this will save us time later on. A lot of times they will actually ask us to write the equation of the asymptotes. Now asymptotes, in this case, are these lines, vertical, horizontal. If you remember, when you write the equation of a vertical line, since x is 0, a vertical line is defined as x equals 0. And the horizontal asymptote, when you have a horizontal line, it's y equals 0. Let's say we have now I told you a little bit ago that asymptotes are such that the graph cannot cross or touch the asymptote. Well, I wasn't telling you the whole truth. Actually, that rule applies when you get to the edges of your graph. That whole idea of end behavior. There are times when in the middle or toward the center of your graph, sometimes the graph can actually cross the asymptote. So for instance, I'm going to draw I should have made this up. So here my graph actually crosses this asymptote, but that's allowed sometimes when it's close to the center of the graph. I can't cross an asymptote when I get at the edges of my graph. So they say this is I would actually have an asymptote, a vertical or a horizontal asymptote at y equals 2. Now if I were to ask for my domain and range, say this is right here, is like at 4. The domain, hopefully you see negative infinity to infinity, What would the range be? Well, the lowest value is negative infinity, and the highest it gets to, looks like it gets up to 4, and then it goes down some, so I would say 4, probably with the bracket. All right. Anyway, so that's the domain of graphs. Now let's talk about how you determine domains of functions or equations. It's related to graphs, but initially it's going to seem very different. So in other words, say we have if you want to, you could think of this as y equals x plus 1. Once again, I like to think of domain as all the possible values of x. So now this is a little different way to think than we had graphs. Here I'm thinking of, okay, let's start plugging in numbers for x. And my question is, what numbers can we plug in for x and have everything be okay? In other words, not break any math rules, not create any trouble. Now for this equation, could I plug in x equals 0? Yeah. Could I plug in x equals 1? Yeah. Could I plug in x equals minus 1? Yeah. As a matter of fact, a better question might be to say, is there any number I can plug in for x that would be a problem? That I would break some math rule, that I do something I shouldn't do? And this case is there is not. So for this one, a lot of times we would say it's all real, or if they want an interval, you would say negative infinity. Now once again, with the equations, they don't usually ask us for the range as much. Mainly they look at domains. Now, so you may ask yourself, well, are there ever any equations or functions where the domain is not all real? And there are actually 2 cases where it happens, and we're going to talk about one now. So here's what I like to do when I'm asked to find the domain of a function. Before I even look at the equation very closely, what I call my default domain, my starting point, my assumption to start with. It may change, but the place to start is when I first have a function or equation, I'm going to assume at first glance, my assumption is it's going to be all real. And a lot of times it is. But not every time. But that's where I'm going to start. I'm going to assume it's all real. And I realize there's only 2 exceptions to this. 2 situations that's going to change this domain from all real. Now the first one we're going to talk about later on in this class. If you ever have your variable or your x under a square root sign. In other words, if this is part of your equation, then that's going to change the domain. Now we're not going to talk about that now, but we will later on. So if you have that, then you know the domain is not going to be all real. It's going to be changed. The other thing you have to look at, and the last thing, there's only 2 things that are going to ever cause this domain to be different than all real. This, and then if you ever have a fraction and you have variables in the denominator, in the bottom, so here's an example. Here's this function or equation. Turns out it's like a fraction. And I do have a variable in the bottom of this function. Once again, even with this one, before I look at it too closely, I'm going to assume by default the domain is all real numbers And then I look for my two exceptions. And as it turns out, I have the second exception here. I have a variable in the denominator. Then I have to say to myself, okay, this is going to cause my domain to change some. Now, in what way is my domain going to change? Well, let's think about this. So what's the big deal about having a variable in the denominator? What could happen? What number could I plug in for x that's going to cause me problems, that's going to break some math rule? And the key is, if you remember in math, you can never, ever, ever have a denominator that equals 0. You're breaking one of the math rules. You cannot divide by 0. As soon as you have a 0 in your denominator, you stop and you're done. You cannot keep doing anything. So if I look at this, then I say, well, my question is, what's the domain? What are all the possible values of x? I'm assuming x can be anything. But now I look at this and I say, well, the thing I have to avoid or be careful about is if the denominator is ever equal to 0. So I say, well, what number could I plug in for x that would cause this denominator to be 0? And you know what? If x ever equals -1, I'd have -1 plus 1, which would be 0. I would have a 0 in my denominator. I can't have that. Therefore, I say, you know what? For this equation, x cannot equal -1. So that's now going to change my domain, because my domain, I assume from the start, is x can be anything. X is all real numbers. Well, because I have a variable in the denominator, that's not going to be true anymore. Instead, it's going to be, okay, my domain can be all real except x cannot be -1. So in a sense, my domain is everything but -1. Okay. That's the way it is. So now, in the next section of what we're covering, we're going to start working with what's called rational expressions. Rational expressions is a fraction made up of a polynomial over a polynomial. Here's an example of a rational expression. So I got variables in the top, variables in the bottom. Because I now have these fractions, one of the things they're going to ask me is what's the domain of these kinds of expressions. So what you're going to do is, basically, the domain is going to be all real except whatever variables would cause the denominator to equal 0. That's the only thing I have to worry about. So let's do some examples. How about if I'm given this function, I'm asked to find the domain. So once again, my starting point for any function or equation is the domain is all real. So I'm going to assume it's all real. And then the only thing I am worried about, there's no square roots here. The only thing I'm worried about is, do I have a variable in the denominator? And I do. Now some people might say, what about the variable in the numerator? I don't care about variables in the numerator. Those are never going to give me a problem. The only thing that's going to give me a problem is if I have a variable in the denominator, because I have to be sure that the denominator never equals 0. So for this equation, what number can x never be equal to? x can never equal 0. If x is 0, all of a sudden I have a fraction with a 0 on the bottom. So what's the domain? All real except x cannot equal 0. Just for fun, here's going back to a polynomial. What's the domain of this? Once again, starting point is the domain is all real numbers. Then I go looking for variables in the denominator. There's not even a denominator here. I'm done. It's pretty simple. Let's do one or two more. How about, let's go back to rational expression, which is what we're going to be starting to work with now. How about given this function and you're asked what's the domain? Well, I start out by saying the domain is all real numbers, and then I look to see, and lo and behold, I do have a variable in the denominator of the fraction, so that's going to change my domain. So now the question is, how is it changed? Now what's interesting is x squared minus 9, it's going to be sort of hard to figure out what values of x cause me a problem. What you always have to do is you need to factor the denominator. Because when I factor it, then it becomes very clear. Once again, I'm looking for what are the values of x that would cause the whole denominator to equal 0. Well, in this case, I've got two parentheses multiplied. So if either one of those parentheses equals 0, then the whole thing is 0. So let's look at the first parenthesis. What value of x would cause that first parenthesis to be 0? Well, when x is negative 3, because negative 3 plus 3 would be 0. So therefore I know from this first parenthesis in the denominator, x cannot equal negative 3. But then I look here, the second parenthesis, and I say, well, what value of x would cause this second parenthesis to be 0? And I realize x cannot be 3. So in this case, there are actually two numbers x cannot be equal to. Because if x is equal to either of these numbers, then I've got a 0 in my denominator. So for this one, I would say the domain is all real except. Now you know what? I think in a lot of the problems, they want set notation. So a lot of times they're going to do this kind of thing. X such that x, and then remember what you do, you just list the numbers that x cannot be. I think they probably want that form when you actually do your online problems. Now here's what's interesting. Let me just do this now while we're here, so when we look at it in a little bit, we won't have to do it again. You know what happens when we figure out which values of x cause the denominator to be 0? In this case, minus 3 and 3. You know what that results in? If we were ever to graph this equation, you know what that results in? Those become vertical asymptotes. Later on, we're going to start with a rational expression, and one of the questions is going to be, what are the vertical asymptotes? The vertical asymptotes are just those values of x that cause the denominator to be 0. Because if we were to try and graph this function, what you do is when you find which values of x cause the denominator to be 0, and those become your vertical asymptotes, in a sense, I have two vertical asymptotes. the line x equals -3 and x equals 3. So we talked about before, vertical asymptotes mean you draw these vertical lines. And that means if I were to go and try and finish this problem and try and figure out what the graph looks like, that means that my graph cannot touch or cross these asymptotes. And these asymptotes spring from looking at the denominator of my fraction. Now, speaking of that, let me go and stop for now, because now the next thing I'm going to do is sneak preview the next video. Earlier we talked about horizontal asymptotes. Horizontal asymptotes also spring when you have usually rational expressions. So the next video we're going to talk about how to determine horizontal asymptotes, and even later on we have a third kind of asymptote, an oblique asymptote. Alright, so we'll talk about these on the next video.